So to continue on, we're visualizing hierarchical structures, which is a graph, again, a trees that are graphs, binary relationships, but they have no cycles, no circuits, and they're fully connected. And last time we looked more or less using spatial layout that is linear. And I think it's time to look what happens if we use a circular layout. There are some advantages to it, and mainly the advantage is that we can put the root in the middle, and then all nodes on level 1, which are the children of the root, they go on around it. But what happens is if you look at the perimeter, the amount of space I have for the root is very, very small, and it's just one node right in the middle. Then as I move away from it, I get more space to lay out nodes. So at this level, the perimeter is a lot larger. In theory, I could lay out more nodes. And I was telling you that trees tend to grow exponentially, pyramid schemes. Grow exponentially. The perimeter doesn't grow exponentially. It's PR, isn't it? 2 pi r. That's the perimeter of the circle. So it's kind of, it grows linearly. So it will still be overwhelmed, but it may be using the space a little bit more efficiently in that way. The next approach is going through, okay, what if we use kind of simulate 3D? Then if you look at it, some part of it is circular layout, part of it is linear. So on this side is linear, and then on the kind of on those 2 dimensions is a circular layout for this. And I have a video for it, and then I'll kind of get back to I'll get back to it afterwards. Sorry. There's not much I can do to group sharing my screen. Lecture slides. By the way, this video is different than that picture in the sense that they rotated it. So the y-axis, in a way, it's the one that's linear, and the circular part is on the x and z.
Visualization called the cone tree shows part of a Unix directory hierarchy. Each node is a directory. When a directory is selected, the tree rotates through the shortest path to bring the selected path to the front. The selected path is highlighted with the directory name. 3D is used to make more effective use of available screen space. A 2D layout of the same tree would not fit on the screen. The user would have to scroll through the 2D layout and wouldn't have a view of the whole tree. The 2D layout could be reduced to fit, but details would be lost. Interactive animation is used to shift some of the user's cognitive load to the human perceptual system. You can see this by looking at a selection done without animation. It takes several seconds to reassimilate the relationships between the parts. With animation, the perceptual system tracks the relationships because of object constancy. When the animation completes, no extra time is needed for reassimilation.
Okay, some interesting things there. First of all, animation helps rather than just move it. Second, he claims that, oh, I can do it in 3D. But I would argue that you cannot see the entire, because in 2D you would have to kind of scroll around and pan and not fit on the screen. But in 3D it doesn't fit on the screen as well. I'm only seeing the nodes that are towards me. I don't see the ones that are in the back. It's just, if we go to Gestalt, the completion, our brain completes the fact that they're in the back, but we don't really see them. They're hidden. In order to see the entire tree, I have to click on them, to keep clicking and navigate and turn it around. So I think that's something in the slides as well. And while I share this, okay, I'm almost there. So on this one, if the tree is relatively complex, we won't be able to see it. It appears like we're seeing it, but we're not. Again, things that are in the back, I can see only these nodes in the front, but the nodes in the back I cannot see. Also, they didn't mention it, but I think it's very useful that they actually have a projection on the bottom. You can see a lot of the tree. They had it in their visualization as well, from still at the bottom, but you could see it. Kind of the light was shining from this way down. So I think that's useful, but again, you're not really seeing the entire tree at the same time. One good thing about 3D is that if you have, if you put your finger really close to your eye, it may look as big as a building that's, 200 yards away. So there's some kind of what I put in there, focus plus context. It's kind of some natural way of getting more real estate to things that are closer to our point of view. And then nodes that are further away, they're like this one, for example, here in the back, it's going to be smaller than nodes that are further towards us. Just naturally, they appear a little bit bigger. So it kind of that's what the 3D perspective really allows us. It's more natural than anything else. It's cool looking. That's the fisheye technique I was talking about. Things that are closer to us naturally appear bigger in 3D. Occlusion still occurs. 3D perspective sometimes tricky to estimate, and it's more complex math. Okay, so since we're playing with a spatial substrate for the most part, that's what I've been doing this since I started. We went to a circular, went to a 3D, circular, linear combination on a 3D. Let's talk about hyperbolic. So there's actually a two-dimensional hyperbolic approach and a three-dimensional hyperbolic approach, and we will look at these when I share my screen. But first, what is hyperbolic space? This is one attempt to represent it in real, kind of with an object that you can touch. But it looks something like this. So it's different than Euclidean space. It's a different distance measure. So some of the things that happen in hyperbolic space, we have, again, not necessarily very useful for trees. I don't think they actually do a complete hyperbolic space when they implemented their tools to visualize trees. But just in general, if you care about hyperbolic space, we have lines that are more than parallel. In a normal space, two lines either intersect, lines are infinite, so they meet somewhere and intersect, or they're parallel. If they're parallel, the distance between them is always the same. In hyperbolic space, as you can see here, these two lines are hyperparallel. And the further they go, the distance between them increases, actually. So it's kind of a weird kind of space to consider. And this is space in terms of mathematics, not in terms of visualization. But it has some, our visualization still uses the screen and the same kind of space anyway. And one other interesting thing is that you can have triangles. And with a triangle in a Euclidean space, if you add the angles between the lines, you get 180 degrees. That's every triangle. Sum up the angles, it's 180. In hyperbolic space, you can get less than 180. interestingly enough. Now, on why do they use hyperbolic space? It turns out that what happens, it behaves kind of that fisheye thing that I was talking about. So what happens really is that things that are in the middle of the screen, they're going to be really big, so I can see all the details. As you go towards the edges, they get really small and into each other. I think that's a more practical way. They don't care about hyper parallel lines or anything like that. It's just that you would see things that get to the edge of the display be really small. I can have 100 nodes look this big, and then in the middle of the screen, a single node would look twice as much as 100 nodes. Okay, so that's kind of why they're doing it. It's another way to not show the entire tree and allow you to kind of navigate and somehow connect the structure, determine the structure of the tree by just navigating through this space, moving it around. So let's see. I'm going to share my screen and we'll look at the 2D one, which is the hyperbolic space. I think I checked this. I hope I have it still installed on this machine. I'm not sure if they redone the computer. Long time ago, I got this StarTree program for Inksight, which was started by, who did the mouse? It's a research lab, very pop. I'm drawing a blank here. Well, maybe it's in the video. Xerox PARC? So it's from Xerox PARC. These guys were researchers at Xerox PARC, and they kind of invented this whole thing, and they tried to commercialize it. They created this company Insight, and that was bought by somebody, and that was bought by somebody, and that was bought by SAP, and the products, most of them disappeared. But I have a video, so while I talk, I'm gonna. So I'll talk about the hyperbolic browser, the 2D version. And for that, I need to go to YouTube. Maybe not. Actually, I don't have YouTube, but I might need to run the StarTree viewer. Sorry. Getting myself confused here. Okay, so this is our hyperbolic space. And like I said, things in the middle take a lot of space. Right here, you can see an entire tree structure gets smaller and smaller as they go towards the back. So again, you kind of get a fisheye kind of effect. Things in the middle, very big. Things at the bottom, towards the edge, they get really small. Notice the entire thing that we looked at is actually squeezed in here right now. I have the installer for this, and there's also, so there's a viewer and there's a builder. Nobody ever used it, but you could use it for a project. I'm not trying to discourage you. It's just a way to do it. If you click on something, you can actually add websites to these nodes. They will open up the website, but notice how this functions. One thing that's a little bit maybe confusing is that children that used to be on the right, if you move them well enough, they kind of switch position and go on the left. I did it on purpose. I moved too fast through it. And with this, I think they have an example where you can add pictures to each node. And as they get really small, you notice how they get so small that you can't see them. I mean, that's the whole thing. That's why we're using, they're calling hyperbolic, but that's the only feature of that space that we're using. So that's the 2D Um, and let me run the videos for the hyperviewer. Sometimes I think she has it as H3. So I have two videos that we run, and then I can. It's also a program that you can. I'm going to run the demo a little bit. It's going to be clearer. The videos are a little bit. Um, and she's explaining everything that's going on. Okay, so starting in 3, 2, 1.
Show the hyperlink structure of a small website using the H3 layout and the H3 viewer drawing algorithms. Both layout and navigation occur in 3D hyperbolic space, which provides a view of a large neighborhood around an easily changeable point of interest. Nodes appear to shrink when they move from the center of the sphere towards the periphery. The entire structure always stays within the confines of the enclosing sphere. When the user clicks on a node, it undergoes an animated transition to the center of the sphere, which includes a rotational component so that its ancestors are on the left and its descendants are on the right. This canonical orientation helps orient the user locally. The user can also rotate the entire structure around the center of the sphere, which helps disambiguate its three-dimensional form.
One more. There are short videos.
Drawing every link in the graph, we are only drawing the links of a spanning tree, which was used as the backbone of the layout algorithm. When we show all the links of the full graph, the view becomes very cluttered. The interactive interface allows the user to select one or many nodes and display all incoming or outgoing links for just those nodes. The non-tree links are drawn with narrower lines than the main spanning tree links. All links are drawn with a subtle color coding to indicate directionality. The reddish end is outgoing and the bluish end is incoming. This effect is understated for individual links, since when the spanning tree alone is drawn, the directionality coding is redundant. However, if many links are drawn, the aggregation of many links can show sources and sinks. In this dataset, many nodes have no or only a few non-tree links. But the table of contents document for the site has a large number of links, both incoming and outgoing. The choice of spanning tree heavily affects the user's mental model of the site.
Okay,
Many
so
graphs, which are relatively heavily
I'm going to stop here. Basically, this view can work for a general graph, but it's mostly for a spanning tree. I mean, that's what they're looking for. And the hyperbolic thing happens on a sphere, and everything is inside of it. So here is the actual program. Nice thing is you don't have to install anything, and it comes with some sample files. I like the call graph is functions that call itself for a program. So here is the top. Somewhere in here you'll find main. This is probably a program written in C, so there's a main function. Here's the main function. Before that function gets called, you can see there's a lot of other functions that happen to be called. So I can rotate this all around. So you can see that main calls a lot of functions in here. It's a very complex structure, and I can pick something. Okay, I picked the graph, another node here. And that's all the thing is, I cannot see this graph all at once. It just gets too small. I have to navigate, just like I had to do with the cone tree, just like I had to do with hyperbolic browser. So anyway, I'm getting lost, But I can click on something and it gets reordered. I'm back to main. So while I go back, I'm also try and check, see if there's more demos before I go back to the slides. No, that's about it. So the hyperbolic browser, they claim they can show about 1,000 nodes in it, and children may change relative orientation. If we go to the 3D, they claim they can show 100,000 nodes. I don't know. I mean, you're not going to be able to see 100,000 no matter what. But it can handle it, I guess, software-wise. So that's the end of node link diagrams. Everything that we did so far was using a node and a link. And now we're moving into space filling technology or techniques, where we try to use pixels. Rather than show each individual link, we use pixels and try to fill each and every pixel. So kind of a little bit what is the problem with node link diagrams? Then talk about tree maps, which pretty much use linear axis, linear spatial substrate. And then radial space filling, like name says, they're going to use a circular substrate for what they're doing. So node link diagram tree that I have represented here, for the most part, you can see that the root is using a lot of white space. I'm trying to draw a rectangle. But basically, you know, if I were to draw it, it'll be this, a lot of white space just for the root up there. Then if I look at the children of the root, they also are 3 of them taking about the same amount of space right here. And then if I go to level 2 children, they're a little bit more efficient and they kind of take also space. So I'm wasting a lot of white space at the root, which are lower numbered, level 0, level 1 of the tree, and so forth. And so the idea of space filling would be to not waste that white space. How do I do that? First of all, what if I take this band and move it inside the root space? So the root now is going to have the children inside of it. And then I can take the last band and move it inside. So I'm going to have 2 nodes in here, 4 nodes in this one, and 1 node right there. So basically, I get rid of 2/3 in this example. It's not true in general, but I get rid of 2/3 of my space that I need because I put children inside their parents inside their parents, and so forth. And I do that recursively. And that's the idea of space filling technique. So now all my pixels are going to be used. Obviously, if I want to use it on a screen, I can use the screen's aspect ratio. So that is the idea of tree maps. Going back to spatial, we're using recursive subdivision of space. It was all the way in lecture 2 that we talked about it, but that's pretty much where it shows up in tree maps. And the way they did it originally, so there's the original way of doing tree maps. Let me kind of pick one. You can kind of see here that I have all the green nodes, and then I have all the blue nodes, and then I have the purple nodes on this side. So if you look at it, first of all, the first, or at least at that level of the tree, they subdivided by breaking it down, chopping it kind of in horizontal stripes. Vertical stripes, chopping it horizontally into pieces. Now, just focus on the green one. The next level of the tree, they kind of chop it off vertically. And then inside of this, they went back to horizontal stripes, and the chopping it up, cutting it horizontal. So that's what I mean by alternating. So that was their first idea. To in order to kind of figure out the levels, you would first kind of break it down horizontally, then break it down vertically, then break it down horizontally again inside, and so forth. And what can I show? So there are really three things. The area of a rectangle can mean something. So this is one node in the tree. I'm just going to pick one up here that's big enough. That is one node in the tree. Inside of it, I have its children, another node. So I can use area. I can make the area proportional to some value that I want to show. So not only that I show I show the relationship, the parent-child relationship in the tree, but I can also use area to show an additional value, an additional data dimension. I can also use color to show yet another data dimension. That's not, again, the child relationship that's shown. All the children are inside their parents. That's how it works. And then notice that there's also labels here, so I could use labels for yet another dimension that is more nominal. I could even put numbers in there, but it's not going to be as clear. You have to read them. Okay, so that's what it used to be, tree maps. That's the first try. Note here that some of these slices are so thin, it's kind of impossible to compare them. The area is there, but it's not. I'm not going to be able to compare them. So the biggest problem with tree maps are thin rectangles, basically rectangles with different aspect ratios. Since area now has a meaning, it's conveying a data dimension. Which one is bigger? Is the red area larger than the green area? We can compare. Our visual system is not good at doing that. If the aspect ratio is not the same, we can compare bars because they have the same width. And then we can compare kind of fat rectangles against other fat rectangles and squares. We can do that. But if the aspect ratio is too wide, too large, they have a difference, we simply can't do it. So that's a problem. So maybe that's the biggest problem there, but at least they have a solution for it. The other problem here is how many levels in the, I mean, I was telling you that this shows the levels of the tree. That's a given, but it also shows extra stuff. But how many levels of the tree can I see? And I'm not sure if it's a problem, it's more of a limitation. So like I said, I can see this 1, 2, 3. Is there a fourth one? Well, and the big root. The root is everything. So about 3 or 4 levels, and then I kind of start to lose the potential to distinguish. Can I show 10? Nah, I don't know. So aspect ratio, length divided by width, or width divided by length, whichever way you want it. So here is they solved that problem by finding new ways of dividing. Like I said, the first attempt, or the first instinct, was to have an area that's proportional to some data value. And they call that slice and dice, very technical. They slice it into, and then they came up with this kind of set of methods. Notice that the rectangles, it's the same data set in all 3 of these. Actually, yeah, it's the same data set in all 3 of these. But notice how much easier is it to compare these versus these in terms of which one is bigger, which one is smaller. And then they came up with these, which are somewhere in the middle. Some of the rectangles here tend to be really long versus kind of almost a square right there. But that's why did they need it? Why did they come up with the middle one? Well, here it is why. In a normal tree, normal meaning in a node link diagram of a tree. Let me scroll up and pick one up. I can show that this is, if it's important, some countries it is. Well, maybe not nowadays, but 100 years ago, it was 200 years ago, it was important. Firstborn. And unless you are in a king, in a royal family, it also matters if you're firstborn. So if you think about it, in this I can show an order, because this is the first, this is the second, this is the third child. This is the first, this is the second, this is the third child. Okay, so there is an order that I'm able to show in a node link diagram. It turns out that whether it's important or not, it doesn't matter. I'm able to show it if I wanted to. In this one, I can easily show the order from left to right in slice and dice. So maybe that is the only advantage of slice and dice. I can show order. The first one is the first, the last one is the last, the middle ones are in the middle. It's pretty clear. The problem with these is that, yes, they have really good aspect ratios. And if you look at the colors, whitish ones are the first among the first, and the black ones are among the last. And then you can kind of see a grayscale as you go. So they have that just to show the order. So in this case, maybe this one of these two is the first one, and then the last one end up being somewhere in here. So there's no order. Without using color to show order, you won't be able to tell which one is first, which one is last. So they kind of, yes, they're able to get really good aspect ratios, but they lose order. And that's why they came up with this third method here, where they can show both order. How is the order shown? Notice it's kind of starting from the top left corner, and as you go down, sorry, I had to click on that thing that pops up. So as you go this way, these come later in the tree. So it emanates from that. It's not 100%. I mean, you don't know if it's going to be a little bit higher or a little bit lower, but the order is kind of generally assumed. It's shown, it's preserved that way. And I actually have a short demo on that, and I will share my screen and we'll see. So pretty much you can see here, slice and dice is the first one, squarified, strip, trim out, and the pivot ones are the ones that are preserving order. So let me color them by order, and then you can kind of run them. What they're doing, I think they're changing the size and they're showing you how fast they're computing. But when they change the size of a node, notice that in the squarified, they kind of tend to jump around. So that's what's happening right now. The size of each node is randomly changed, and the tree is redrawn. The order of the node stays the same. So you're seeing that the squarified does not preserve order. That you can kind of see that in an animation. These other ones tend to preserve order. So the whites kind of are in the top left corner. So that's pretty much all there is here. Now on the tree map that you have to use for the homework, it's this piece of software. I took it, I unzipped it here. And you don't need to run it with a command prompt. You can either do the run.bat, or on some operating system, you just click on the jar file. Tells you it's not non-commercial. Again, it's HCIL, University of Maryland. Let's get some, and these are the TM3 file and TMS. Like I told you, the difference would be that TMS knows what you want to use your color for and so forth. TM3 is pure data. And here is how TreeMap kind of loads it. And again, don't expect that when you load somebody else's TM3 file, you will see their snapshots, because you won't. You're just going to see it like that. All you have to do is check that it loads without an error. And here is the main tab. Here's the legend tab, filters, and hierarchy. Okay, so on main, notice that this is qualified right now. So it's some NBA players. If you want to look at the data, here are data attributes, players, minutes played, points, rebounds, and so forth. So it's something about basketball data. So there's quite a lot of, notice that it's not necessarily a tree representation. And that's kind of a nice thing about TreeMap, is that it does not necessarily, you don't have to have data in a tree format. You can, and we'll talk about it. We have about 7 more minutes, so hopefully I'll get to it. You don't actually need it. What I talk about is what you need in the homework. You can set up your own tree hierarchy if you want to. And even if I don't cover it today, I'll cover it starting next time, but you don't need that for the homework. So the homework just pulls up data in just the format, pretty much in a table format. And then you can make it treat things as if it were a tree. Remember when we looked at hotels that have pools and restaurants and so forth? It's kind of the same thing. That data is really a table, but we looked at it in the past as if it were a relation, Venn diagrams and so forth. The same thing here. This data is normal data that we've used so far, but I can look at it as if it's a tree. So right now, there is no structure. I have my root, which is the entire file, and then these are all the children. If you want to play with it, here is slice and dice. Not very useful. These are all the players there. Strip and so forth. Now, again, some things you can do, you can decrease the font size, increase it. Again, border padding, you can add more padding to it. It's going to make more sense later on. Okay, so on the legend, right now they show the name of the player. And the size, let's say the size can represent number of games played. You see there's players here that didn't play much. There's players here that played a lot. And I can use color to represent, that's why I want this legend tab, because I can understand what I'm looking at. For example, I can use this to show the team. And it's kind of an older data set. It comes with TreeMap. But here are the teams at the time. Again, not the best use of color, but they're trying. And you can see all the players. Not the best view. One thing I can do is start putting a hierarchy in place. And things are not showing properly here. Let me see. Hierarchy 1. I think my resolution is really low. I don't know how do I fix that. There, I have my attributes right here, but I can't see them, unfortunately, at this point. I will try to change the resolution, which may mess up the Blackboard Collaborate. I apologize if that's the case. We're 4 minutes from the end of class, so I will stop recording. But this is not fitting it within the resolution that I have, which kind of works for presentation. Let's see, display. Resolution is not too bad. I don't know why it's taking so much space. It won't let me change it. Okay, on this one, it is a little bit Okay, so in order to show you this, I need to see the inside of this. Where it says hierarchy 1, attribute values, type of binning, I need to be able to get inside and see it, and it won't let me. Just because, what can I do? I need to stretch it. Vertically. Okay. I kind of artificially stretched it out. And you can see what I was getting at. So I can go here and say, let's see, we can break them down by conference, which doesn't show up. Here are the attributes. So I can take conference and add it here. And what happened is that I have one more level in my tree. I have the two conferences, Western and Eastern Conference. Right now I can see player within the conferences. I can also, if I'm not happy with that, oh, okay, let's see. I destroyed my, okay, here again. I can take the team and add it. So now I can see the conferences and each team. Obviously the colors now look a lot better because they're inside their own teams. So I can take and look at the players inside each team. And obviously most teams play about the same amount of time, so when you look at them, the teams, the amount of time is very similar. I mean, I don't visually see much difference between teams in here. Well, maybe some played an extra game or so for the finals or playoffs and so. But that's how I can create my own hierarchy. Again, the data set is really a comma separated value, and the hierarchy is created in this manner. So let's see, we're kind of out of time, so I will extend this homework. If you want to get started, get started. One more minute to kind of point you in the right direction if you want to get started and get a head start, but I will extend it for one more week. Follow this link and go to the documentation. The applet doesn't work anymore because no browser supports it, but you have the actual Java application. So they do have videos. They tend to take too long for me, but you can go to create your own data file. Notice that it's an Excel spreadsheet. It just has two special, if you read through it, and I'll talk about it next time. It has two special things that you put, which are your data sets, like length in miles, traffic lights, speed, kind of the name of the attribute and what data type you can use. There aren't that many data types they recognize. And here is kind of how it shows up in the view. So you're going to have to create your TM3 file to look like this. None of the FG and H matters. We're not using it for this homework. So that's when you want to put your own hierarchy in place. So with that being said, again, I will extend the homework but I will cover, we'll start right here next time. And let me find